Okay, so it's our pleasure to have Dan Pomerleano, and he's going to tell us about the quantum connection, Fourier Laplace transform, and families of infinity categories. Okay.
All right. Thank you for inviting me. I'm sorry I couldn't participate more in the meeting with the time difference, but it looked like it was some really interesting stuff was discussed. So my talk's going to go in a little bit of a different direction. I'm going to start by speaking about the quantum connection, which is something that I actually know relatively little about as well. So if I make mistakes, I'm sorry, but you'll see that we'll start with the quantum connection, but we'll come to subjects that are more central to the topic of the conference, to log Calabi-Yaos and symplectic homology and stuff. But let's start with just to remind you guys about the definition of the quantum connection. So the setting we're gonna take is we're gonna consider the simplest version of the quantum connection, where you have a monotone symplectic manifold. That means the symplectic form is exactly, the class of the symplectic form is the same as C1. And the quantum connection is going to be a one-parameter quantum connection. So meaning you're only going to differentiate in the direction of a single. You're going to use a single Novikov variable Q, and we're only going to differentiate in the direction of Q. So this is the sort of standard formula. Why it's like that? Well, if you have one variable, it might be a little mysterious, but if you have multiple variables, then this flatness of this connection is closely related to associativity of the quantum product. So the small quantum product, the version that I'm going to use is just sort of the version that's linear over Q. So you have sort of the classical part, which is the 0th order part, the first order part, which is gonna, use only holomorphic curves with area 1. Then you have a part that uses holomorphic curves with area 2, and so forth. So it's a polynomial product because of the monotone condition. If you look at this connection, you see the Q to the -1 part, and you think maybe it has a pole of some kind at Q equals 0. But it's not so clear, maybe because also this additional, it's not exactly clear what's going on because of this additional Q dependence of the product. So there's a way to sort of simplify the connection a little bit. So, if you take a grading operator, which means you take every cohomology class and you multiply it by, I guess in this case, 2 times the floor function of the grading of X over 2. So if X has an even degree, that's just multiplying it by the degree. Otherwise, it's slightly different, but that's all right. So we multiply it by X. So then the quantum connection, you can do a gauge transformation, and you'll have to sort of take my word for this formula. It's not too hard if you think about it a bit. So it simplifies to have this form over here. And what's nice about this form is that indeed you can see that you have a pole. This term gives you a pole, and then this term here, no longer depends on Q. So what this multiplication, when I put the *1 here, what that means is it means to do the usual quantum product and then just set all of the Q parameters equal to 1. And that's valid because of the polynomiality of this quantum product. So at Q equals 0, you have a pole, a simple pole, and its monodromy and everything is really easy to understand because it's basically just given, the pole term is incredibly simple. It's just this grading operator, basically. Now, the more interesting part of this connection actually occurs at Q equals infinity. So to to sort of get our hands on that, you want to change variables to q equals 1 over q, and you know the basic equation is that minus, you know, if you do that, minus q squared ddq will be the new dq. So we take our quantum connection and multiply it by minus q squared. And what, you know, in the first form, it translates to something like this. So in the first form, the form that I gave it to you originally, it translates to this one here. And then in the more transparent form, it translates to this one. And so this one you can see has a pole now of order 2. And connections, formal connections with a pole of order 2 are sort of a very classical subject in France. I don't know. I mean, Malgrange has a book, Deline, I think. So there's a well-studied thing. And so the question is, what is the nature of this singularity? So so here's the conjecture of, I guess, there, you know, you'll find this one in KKP. Now, the KKP version, they don't assume anything about phono-ness, and they use a multi-parameter version of the quantum connection. So it's a bit more complicated. KKP is, sorry, Kontsevich, Kosarkov, Pantev, their paper on non-commutative Hodge theory. And also you'll find this in sort of Galkin and Iritani's, Galkin, Goleschev, and Iritani's, so the gamma conjecture paper. And so the conjecture is this, that, and I'll explain what these words mean, at least the first part. So the quantum connection, it has a singularity of unramified exponential type at q equals infinity. So it's basically saying that this second order pole is particularly nice, and the regularized formal monodromies at q equals infinity are quasi-unipotent, meaning they have eigenvalues which are roots of unity. So let me try to explain what at least these words mean, and then also how they fit into why they're, you know, why it's a little bit about why it's an interesting conjecture. So so if you take a formal meromorphic connection, something like this, where you have a matrix in this formal field of fractions about 0, the formal punctured disk, then so you can act on these by gauge transformations. So the question is to, you know, there's a classical theory of how to classify connections up to gauge transformation. So we say that you have a regular singular point if by a formal gauge transformation it can be transformed to have a pole of order -1. And so that's sort of the simplest kind of singularity. The next simplest kind of singularity is this unramified exponential type, which is what's relevant when you have a pole of order 2. So it says that you get a direct sum decomposition of the following form, where that the connection breaks up into pieces where you have a regular part called the regularized connection, and then you add sort of the dumbest, or, you know, the simplest form of an order 2 pole, so that lambda k is just some number, and so it sort of says that the order 2 pole is as simple as possible, and the significance of that is there's a whole theory about these about these connections of exponential type. So you assume you have something like a connection of exponential type, then what you can do is actually this decomposition, there's an analytical theory. I think the names that go with this are Levelt, Turitin, and maybe there's one more name that I'm forgetting, but I think sometimes it's just referred to by these authors. You can find it in almost any book. Like say Sabah has a book. Sabah has a book about Frobenius manifolds. You can find it discussed in there, for example. But what their theorem says is that you can actually lift this decomposition then to certain sectors in the complex plane. So it's not, you start with something formal, and then the decomposition will sort of lift uniquely to an analytic decomposition. And then the analytic, so these sectors have they're centered about some, there's certain directions that you have to avoid, but you have these sectors, and they have, maybe that's a bad way to draw it. Sorry, they're wider than so you have some sector here. Whoops. So you're about some angle phi, and you take up slightly more than pi of your complex pi degrees. And then if you have another such sector, it'll overlap with the sector in some amount. So you take another sector like this, and then they'll have some overlap. And the idea of Dubrovin's conjecture is basically relating. So when you have an overlap like this, you get sort of an analytic continuation between the flat sections of the connections. And so Dubrovin's conjecture is basically about relating pairings in topological K-theory with these analytic continuations, which are called Stokes matrices. So this is probably a bit, we could spend a long time on this, but I just want to sort of explain, this is what this conjecture does, basically, is it allows you to state this Dubrovin's conjecture. And typically, Dubrovin's conjecture, in Dubrovin's papers, he studies the case where the eigenvalues of the quantum connection are all, where the quantum multiplication by C1 is semi-simple. And in that case, it's automatically, it's not obvious, but it's automatically of unramified exponential type. So this condition is automatic. So, but in the cases where, to extend that conjecture to Fano manifolds where the multiplication by C1 is not semi-simple, you need first this unramified exponential type, and then you can state the appropriate form of the conjecture in that case. So you can find a lot more about that in Golizhev, Galkin, Golizhev, and Yuritani's paper, for example. That's a good reference for this. So we're going to try to think about, so the goal is to sort of explain some program to try to prove this conjecture. I should have said, by the way, maybe I didn't say that. I put it on the screen. This is all a joint project with Paul Zeidel. So I should have said that explicitly. So let's say you have the algebra of differential operators. And so it's, it's just the thing where you have two generated by Q and DDQ, and you have this commutator relation. And so a module is holonomic if it's finitely generated. And for every x, there's some non-zero polynomial in Q and DDQ, which annihilates that variable. So sorry, this shouldn't. I was going to state the. so if you have a holonomic D module, what you can show is that, so the simplest case of a D module is where you have a vector bundle and you have a connection. So you choose some basis and you have a connection. That's sort of the simplest case of a D module. And what you can show is if you have a holonomic D module, then you can remove finitely many points. There are finitely many singularities, so to speak, of the D module, so that when you localize it, localization makes sense for D modules, then it's isomorphic to a vector bundle with a connection on it. So the singularities, so once you have something like this, it makes sense to talk about the singularity at every singularity in this sense, because you can sort of go locally about that point. It makes sense to talk about the singularity of the D module in the formal sense that I wrote on a couple of slides ago. So we say that a D module has regular singularities if all of those singular points, when you go sort of formally locally near those points, it's, the corresponding meromorphic connection is, has a pole, can be transformed to something that has a pole of order at most 1. So, so here's the, so I guess you can't really see it. I'm just going to transform it like this for a second so you can see the bottom of the slide. Maybe there's a better way to do that. Is there a better way that I should do that?
I think if you just move it a little bit further up so that the Fourier transform.
Just I can, maybe I can, well, yeah, I can start to, yeah, there we go. That looks better. Okay, so if you have another formal variable, there's something called the Fourier transform. So T is another formal variable. So there's something you can do where you basically interchange the role of DDQ and Q. So if you look at the commutator relation in the ring of differential operators, there's an obvious sort of symmetry where you swap Q and DDQ, but then you have to, because it's a commutator, you have to multiply by -1. But there's an obvious sort of, basically you can swap the role of DDQ and Q. This is called the Fourier Laplace transform. And, let's say you can do the corresponding thing on modules, which is just to say, if you have a module over, say, in the WT module, you can get an NQ module by just taking the same vector space and viewing it as a module over WQ. And this sort of obviously preserves holonomicity because, what's the condition for holonomicity? That there's some polynomial that annihilates, polynomial Q and DDQ that annihilates every vector. And that's obviously, if you just swap Q and DDQ, you'll get another polynomial that annihilates every element. So it preserves holonomicity. And the Fourier transform, what it does is it takes, so let's say you start with a holonomic module, WT module, with only regular singularities in the sense that I explained a moment ago. Then if you make its Fourier Laplace transform, then you get something which is exactly of the form that we predict for the quantum connection. Namely, it has, it's non-singular on the C star, on the away from 0 and infinity. And if you look at the associated connection, nabla Q, so you get a connection away from, you get a meromorphic connection over C, if you like, or you get something that's well defined. You get an honest connection over C star. So if you look at the associated connection, then it has a regular singular point at Q equals 0, and a singular, meaning, and it has a pole of order 1, basically, and it has a singularity of unramified exponential type at q equals infinity. So the idea that we have here is to try to take some module with only regular singularities in some t plane, make a Fourier transform, and try to show that that's the quantum connection. So it's easier to sort of work with, try to construct something which is only regular singularities, and do a Fourier transform and try to prove that that's the thing that we're after, the quantum connection. So here's how that works on the, let me show you how that works on the B side of mirror symmetry. So now we're going to get closer to the topic, to mirror symmetry and so on. So let's say that you have a proper Landau-Ginzburg model. So a function to A1, that's sort of the mirror, roughly speaking, to a Fano variety. I mean, I guess, you know, and maybe you'd say the mirror is not necessarily proper, but this is going to work best for, this is going to be the best analogy for what we're going to do here. And so the mirror to quantum homology is the so-called Gauss-Monen system. So what you do is you take differential forms and you adjoin a variable q, and you equip it with this twisted de Rham differential. So you know, so you do the ordinary differential, but then you also do wedging with dw. And you know, this is probably maybe more familiar in the context of how to say, if you forget q, but forgetting q actually a better way to think about forgetting q is actually inverting q, because q here is, we're thinking of it as a variable of the quantum parameters being a variable of degree 2. So if you invert q, that's basically like making the de Rham complex 2 periodic. And then you can kind of just say, forget about, you know, set q equal to 1 kind of, or look at only the degree 0 and degree 1 part. So it's probably the version where q is inverted is probably more familiar as the how to say, the Hochschild homology of matrix factorizations. But in any event, this thing carries an endomorphism, which is as follows. So you multiply by you do differentiation in theta, and then you subtract multiplication by w. And when you do this thing becomes a this makes it into a WQ module. And in each degree, it's actually a holonomic. It's not easy to prove it. If you have to take hypercohomology first. But it's not incredibly easy to prove, but it follows from the general theory of D modules that this is a holonomic D module. Basically this has some interpretation that's more intrinsic, and then there's a theory about there's a kind of push forward in D modules, and there's a kind of theory that tells you that push forward always preserves holonomicity.
So what is this? So I did not. What is this endomorphism? Where did you
Can I couldn't hear the actual question.
What is this endomorphism? Where did it come from? What is it?
Where did it come from? Well, okay. That's a fair question. For me, it comes from it's kind of I guess here's one way to there are two ways to say it. In algebraic geometry, Q is actually the so for algebraic geometers, multiplication by Q is actually the more natural differential operator. And this endomorphism is what they get is that corresponds to the action of A1 on this Gauss-Monen system. So from the D module point of view, Q is actually the differential operator, and this one is actually just because it has this term which should remind you of multiplying by the base, and then this term is what makes it into. You need this term to actually get a chain map. Otherwise, it wouldn't be a chain map. But another answer to that would be that coming from non-commutative geometry, I'll give that one maybe a little bit later on. Maybe that'll clarify it a little bit. But yeah, this. I'm saying if you just multiply by W, you wouldn't actually get a chain map, I guess. So maybe that's the simplest answer. You definitely wouldn't get a WQ module structure.
Some kind of deformed, like maybe CP2 with a elliptic curve, you consider this Simplex homology, and then you deform, and then you get S1 equivalent.
Yeah, that's where we're headed with this. Yeah.
Okay, so maybe sorry, maybe I was poor.
Yeah, that's where we're headed with this. I think both of us are more in the symplectic homology than D modules. So maybe if you're a D module theorist, you have something nice to say about that. But maybe I'll just push on and I think that'll clarify it for this audience. So the idea is, the claim is that this one has the correct singularities, and here now when I make this statement here, as I said in the D module theory, Q is actually the natural differential operator. So they really think of this, if we look at this, we see DDQ and we think that's supposed to be the differential operator, and multiplication by Q, we view it in the Q DDQ plane. In the D module theory, they're really viewing it in the T DDT plane, where this is actually the action of A1. So this would be your T, and this would be your DDT. Sorry, just multiplication by Q. Roughly speaking. And so the theorem is that this module here has a regular singularity at Q equals 0 and a singularity of unramified exponential type at Q equals infinity. And so the way that this is proven is, so if you have something that's non-singular, then basically this you can prove that this Gauss-Monen system is gives you just this sort of standard the standard Gauss-Monen system, in the sense that you learn in, say, Voisin's book, like a vector bundle with a connection where all the cohomologies of the fibers have the same rank, and you get sort of a local system in that way. And the point is, then once you make this identification, but when you make this identification, we're thinking of this one. What's the connection? The Gauss-Monen connection on this side. The Gauss-Monen connection is multiplication by Q. So we're really on the Fourier transform side. So so if you want, you can say, depending upon how exactly you think of this one, you could say that EQ is the Fourier transform of the Gauss-Monen connection, and then and then you applied sort of a very famous theorem of various people, Griffiths, Groth, and Dieck, that says that this Gauss-Monen connection has regular singularities if you're looking at a smooth family. And so, so these are the two sort of steps that you need. You need to be able to make an identification like this, and then you need to be able to apply a monodromy theorem to get the result. So that's on the AG side, on the algebraic geometry side. Let's say we wanted to mimic this proof idea for Fukaya categories. So this goes in the direction that Umut already anticipated, and indeed his work is very central to this one. So the idea is, so the plan is only going to work if you have a smooth anti-canonical divisor in M, which I don't know, that's a restriction in Fano manifolds, I guess. But even for algebraic Fano varieties, and we're going to let X be the complement of M minus D, and so the symplectic homology is, we're going to study its symplectic homology and the Rapp-Fukaya category, and we're going to try to construct an analog of this Gauss-Monen system, and then carry out the plan, some sort of mirror to the plan, to the proof sketch on the previous slide. So probably a lot of I discussed a lot of this conference. I don't really know because unfortunately I couldn't participate that much. But this degree 0 symplectic homology of X, of this complement, carries a distinguished element from the compactification. So the general idea, if you haven't seen it before, is that you sort of have a periodic orbit in the interior X, and you sort of count certain solutions of a deformed holomorphic curve equation that intersect the divisor at exactly one point. And on the algebrogeometric side, these are, if you use sort of algebrogeometric replacements or conjecturally equivalent things, like in intrinsic mirror symmetry, these are sort of the theta functions, and otherwise they've been studied by various people in symplectic geometry, notably Borman, Sheridan, Barlagunas. And so this class measures how basically the Floer theory in X, if you take X, how Floer theory changes when you compactify it, the complement to the compact thing M. And so another sort of feature that it's actually something that I have a paper as well on, somewhat recent, about a year ago. There's a shadow of commutativity that seems to be really important, subtle, but kind of important for doing these constructions, which is that you can choose a non-negative model for symplectic homology. I mean, you can get away with just saying the cohomologies are non-negative, but you definitely need something like this in order to do what I want to do. And it sort of corresponds to the fact that Hochschild homology of a variety, it lives in non-negative degrees. And so you can find a model where the symplectic homology lives in finitely many non-negative degrees. So that's going to play. I think it's an important shadow of algebraic geometry on the mirror side. So these are the two basic things that we want to use, and so you might not find any. This is an often asserted claim, but not, maybe never appearing in the literature. But part of our paper is to, part of it is to construct something like this. So the symplectic homology carries an L infinity structure, and this, if you take this rigid model for it, then theta gives a Mark-Cartan element, just because there's no room for any other. If you can't go higher, if you had a higher power of q, in order to make something of total degree 2, you would need something in degree -2, and that's you can find a model where that just doesn't exist. So you can I mean, if you wanted to avoid doing this at the chain level, you could say you can do a perturbation lemma and say that there will be a unique Mark-Cartan solution lifting this at the level, kind of at the level of cohomology, or whose leading order term is the Borman-Sheridan-Varagunas class. But I'm just, to keep it simple, I'm going to do it like this. And you get a deformed version of symplectic. Anytime you have an L-infinity structure in a Mark-Cartan solution, its whole role in life is just to twist the symplectic homology. So you can deform it by twisting the symplectic homology in this standard way. Now, in this case, because of the boundedness is actually crucial. Maybe not the non-negativity at the chain level, but the boundedness tells you that this is actually, this thing over here will actually be polynomial. Typically, you would need sort of power series, but here this is actually a polynomial construction, and so there you can do variations on this. You can invert Q, which corresponds to what we were saying before, where you if you take the Gauss-Monen system and you invert Q, you get sort of the Hochschild homology of matrix factorizations, and you can also do this other thing where you look at this one and you quotient out by this SC star Q, and you get just things with negative powers, and that's also an interesting thing. So okay, so now we're able to state the conjecture of Borman-Sheridan-Varagunas, that we're going to that's going to be an input into our approach. So for a Fano manifold, you can actually make it simple normal crossings. Instead of having a single one of these theta functions, you have a theta function for every divisor, and you sum them all up. That gives you the theta function for the total theta function, if you like. And so what they conjecture is that you do this deformed symplectic homology, and that's going to be the quantum homology. And they've proven some version of it. They have some very, basically, this thing has a bit of a complicated history. Strom and Nick announced some program to do this several years back, and then Borman-Sheridan-Varagunas carried out a very significant portion of it, basically the geometric aspect of it, but they haven't yet, I guess maybe that's coming, but they haven't yet made the connection with L-infinities, the algebra. They proved that quantum homology is some sort of deformation of symplectic homology, but they don't make the connection to L-infinity structures. There's some chain complex, which is a deformation that computes quantum homology, but it's not, they haven't brought in the L-infinity structures, but that's fine. We're going to take that as a conjecture for now. There's actually, I can't resist making a variant of this, where, so in the BSV work, it's very important that you have a monotone thing. You can see that right away, because as I was saying, the deformed symplectic homology has this polynomiality to it, and the quantum homology for a Fano manifold also has this polynomiality to it. So there's a match there. But if you take a more general log-Calabi-Yau pair, it wouldn't actually have this polynomiality to it. The quantum homology would be really over the Nabokov ring, and so it doesn't really make sense that you would have that you could, there's some basic problems with trying to do it in general. you know, I think that this deformed symplectic homology still has a right to exist independently of quantum, or maybe there's some more complicated relation with quantum homology, but it should carry TQFT operations basically. And so if it carries TQFT operations, then that will mean that it's finite dimensional over C adjoins QQ inverse, which is going to be enough to do what I want. So I mean, yeah, it's going to be enough to do most of what I want. So so going forward, we'll take one of these conjectures, either that you have some TQFT structure on this deformed symplectic homology, or the full Borman-Sheridan-Valgunis conjecture. We'll take that as an input. You know, as I said, I think BSV have a pretty good idea how to prove it if they haven't written it down already. So hopefully it's not too much of an assumption. So there are similar structures which exist now on the open string side, which you know, so if you have one of these Markov-Cartan elements, then what, you know, the open close, yeah, in this case I want the close to the open. So from symplectic homology to the Hochschild cohomology, I can basically transfer it. You know, this map preserves the L infinity structures, so you can basically transfer a Markov-Cartan solution on one to a Markov-Cartan solution on the other. And they're sort of you know, this Hochschild cohomology, it has a DGALA structure, so that's why it makes sense to talk about Markov-Cartan solutions, and it has a DGA structure. So, oops, the Hochschild chains. So the Hochschild homology is a module over the Hochschild cochains in two different ways, you know, in both of these senses. So it has one Lie module structure, and it has an ordinary module structure, which is known as maybe more well known as the cap product. So, you know, if I wrote down the formulas for this, we'd all go crazy. They're long formulas, but this is sort of the basic picture of what you have. And so you can use that. If you have a Markov-Cartan element, you can also twist not only the Hochschild cohomology, but also the Hochschild homology. So so the Hochschild cohomology is twisted in by just bracketing by this further bracketing by this Markov-Cartan element. You know, even the Hochschild differential itself uses the bracket basically to define. It's basically bracketing with whatever your original A infinity structure is. So if you add terms to your A infinity structure, it's just bracketing with these additional terms. In Hochschild homology, it's the same thing. Like the original differential on the Hochschild homology complex is this Lie action by the A infinity structure. And so if you're going to add terms to that A infinity structure, you just do the Lie action with those additional pieces. So that's what we have on you have deformed Hochschild homology and Hochschild cohomology. And as Umut was sort of anticipating, you also can do it in cyclic homology. So cyclic homology also, so this the version of cyclic homology that I'm using here is the sometimes called negative cyclic homology. It's the version where you use sort of power series in U. U is another variable of degree 2. And as before, the Hochschild cochains, they act in two different ways on this cyclic homology. So they act sort of there's a Lie action which is actually given by exactly the same formula as the Lie action on Hochschild homology, but extended U linearly. And then there's also the other action which is the DGA action, which is So to order 0 in U, it's the original thing, the cap product, but then it has an additional correction term which is first order in U to actually make it commute with B and everything, with the cyclic differential. So you get deformed cyclic invariance. And so B here is the conn operator. I should at least clarify my notation. And so you have this deformed negative cyclic homology, and you also have the periodic cyclic homology, which is where you invert U. So that makes it 2 periodic because U has degree 2. So it's again similar to what I was talking about earlier. If you take a variable degree 2 and you invert U, you kind of make a 2 periodic module. And it carries a connection. That's sort of the classical thing due to Getzler, is it carries a connection, which this is how you do it. The leading part is U ddq, and this sort of funny part over here is going to be given by what you do is you take the derivative of the Mark-Cartan element in Q, and then you apply this this module action that I spoke about a moment ago. And it turns out that this defines a chain map. It defines so it obviously defines a connection just by, well, it defines a connection in the U ddq direction. If you want a connection in the Q direction, you actually have to pass to this periodic cyclic homology and invert U. So that's sort of the supposed to be the replacement of the sort of, at least maybe the Fourier transform of the Gauss-Monen system. So Umut, you asked what's the meaning of that action? It's supposed to be basically going to be this one on deformed symplectic homology, deformed S1 equivariant symplectic homology. So here's what we've got. So this is the work that we have, the result. So let's define the Gauss-Monen system to be this. Sorry, and I want to I've inverted U precisely so that I have an actual connection in the Q direction. Then, if you assume that either one of these conjectures, then the Gauss-Monen system is a holonomic WQ module, is a holonomic D module of exponential type. And okay, so as Umut was saying, so there's some purely closed string analog of this construction. And it's a bit complicated to explain because you need, just like the Lie action in Hochschild homology is really simple. It's just the actual Lie bracket. But on S1 equivariant, on symplectic homology, it becomes this L infinity structure. The formulas become a lot more complicated. So I'm not actually going to go into it because I can state the result. I can at least state the result just on the open string side. But basically, you can build something that maps to this one under open close maps, and the conjecture is that gives you the quantum connection. And so it's an S1 equivariant version of the Borman-Sheridan-Baralgunis conjecture. And so if you take this theorem and then you also prove this conjecture B, then you have this exponential type conjecture for the quantum connection. So that's the program. Obviously, this is just a piece of it. This is also a substantial undertaking, but I think the hope is that Borman, Sheridan, and Varalgunas have this, at least the non-equivariant version under good control. The equivariant version, I don't think anybody's really looked at it. One thing I can say actually about the equivariant version is that if you take what's already in the first paper of Borman, Sheridan, Varalgunas, and you do it S1 equivariantly, it doesn't really make a difference. It goes through the same way. So the first step, at least, in the program, in their program, works equally well for S1 equivariant symplectic homology as for ordinary, as for the ordinary symplectic homology. I guess they just we're not thinking of it or not interested in that, but that's there's a chance that this is going to work out basically. Okay, so how are we going to do this anyway? So what's the idea here? And so the idea is we're going to try to carry out this plan. And obviously, if you go back to the plan, to the proof on the B side, the main engine that was making it work was this classical fact of all these famous people, Grothendieck, Griffiths, etc., Katz, the monodromy theorem for families of proper smooth families of algebraic varieties over a curve. And so what we're going to do is we're just going to luckily for us, there's a non-commutative version of this one. So and this was proved by Petrov, Weintraub, and Bologodsky in a beautiful paper. So you have the algebra of functions on a smooth irreducible curve, and A is going to be a DG algebra over that. So it's going to be strictly linear over that, and a free R module, let's say for simplicity. Then you say that A is proper if its cohomology is finally generated as an R module, and A is smooth if A is perfect as a bimodule. If you're familiar with non-commutative geometry, this makes perfect sense to you. If you're not, at least for properness, you might want to think of the fact that on a family of algebraic varieties, a proper family of algebraic varieties, if you push forward, if you do sheaf cohomology, you always get a coherent sheaf over the base. So here's the so this is the result they have. They have that this should be an affine. This should be an affine curve. I didn't clarify. So what they prove is that if it satisfies these conditions, then the Getzler connection, again, basically, I should say the Getzler connection, if you look at it, what do you do? It works as well for families over some, any kind of curve. This is the Q direction, but if you had some family over T over some variable, then you can actually, it's the same formula basically with DDT. So this also carries a Getzler Gauss-Monen connection, and that only has regular singularity. So that's the theorem that's proved by these people. And obviously, one thing it uses is going to be a degeneration. So it uses Calayden's degeneration statement because, what does it mean to be a connection? It means that you're really you're a vector bundle over the curve. So you need that all the ranks are the same, which is a kind of Hodge-Duram degeneration fact. So Calayden's work. What goes into this is really Calayden's work over this R, and they prove analogs of they model some famous characteristic P proof due to Katz. And carry it out in non-commutative geometry. That's a beautiful paper. So turning to our story here, so many of the conditions that you need to apply the monodromy theorem turn out to be in place already. So you have the degree 0 symplectic homology is a polynomial in one variable over these famous theta functions or Borman-Chard and Valgunis classes, and the wrapped category is further proper over this, meaning proper is understood in the same sense that if you take the cohomology, the total cohomologies of endomorphisms, all of them are finitely generated modules over this C theta. So that's good. And then the other thing, which is kind of in my paper as well, this old paper, is that, but with Paul we do it in a more explicit way. But it's basically, it says that what you can do is you can take this wrapped category and you can strictify it to make it into something that's strictly linear over the Borman-Chard class, over the C adjoins theta. Borman-Chard and Valgunis, apologies. And then in a way that the Mark-Cartan element just becomes, the strict Q theta, just like it was in symplectic homology. And what allows you to do this is again the fact that this non-negativity of the symplectic homology, which as I was saying is sort of subtle, but it seems to be kind of important to the story, to mirror symmetry. So the first question when you're trying to imply the monodromy theorem is, so in algebraic geometry, it's sort of obvious that things are generically, any proper family basically will be generically smooth. So you can always remove finitely many points and get something which fits into the thing that Monen or whoever actually thought about, Gauss, I don't know. But in non-commutative geometry, that's not, I mean, I don't know a counterexample, but there's no reason that should work. If you have a resolution over some ring, it doesn't necessarily give you a resolution over another, the bimod in this C adjoint. It's not going to necessarily be theta linear. So that's the first question you need to answer, is why is that true? And the second question you need to answer is, this thing about the Fourier transform. So why is the thing that we got, if you do so we had our Q DDQ structure. Why should Q, if you localize a little bit, why should Q be basically the DDT operator, the operator, or the DD theta, the operator in the sense that we need to apply the monodromy theorem? So these are the two sort of questions, and the answer to these is mostly algebraic, although there's some geometry that comes in here. So the first part is a purely algebraic thing. So basically, I have 2 minutes, so I better hurry up. There's kind of a magic resolution that solves all of your algebraic problems. And it's sort of a low technology version of ideas in Pragel's thesis. And basically what you get is you're looking for a resolution. So you replace A by this better behaved, by something which is free over C adjoins T. And what you get is that there's basically some very small resolution of the diagonal bimodule as an AT tensored over C adjoins T. That's sort of crucial, AT op module, and it carries a variable Q here, and that Q actually turns out to be basically the quantum parameter. So I guess I don't have time to really describe how you get there. It's not very hard, but you can ask me about it online, at some other point. But what you get from it are quasi-isomorphisms between the deformed Hochschild cohomology and the Hochschild cohomology as a C adjoins T of A of T as a C adjoins T linear category. And similarly, you get a more importantly, you get an isomorphism between the deformed Hochschild homology in the Q direction and the thing that's actually, the purview of the Petrov, Weintraub, and Bologodsky theorem, the C adjoins T linear Hochschild homology. And this does all kinds of wonderful things. For example, from that you can prove that if there, basically that if there's a polynomial such that when you invert Q, so you multiply by Q and you apply this polynomial, if that vanishes, then then the localized category is actually smooth over the curve. And just to finish, just to say where the BSV conjecture comes in, if you want to prove this basically comes down to, when you invert Q, the deformed Hochschild homology is going to be the quantum homology. And this P adjoins theta is basically just the characteristic polynomial. So it just, you have that thing is finite dimensional, so there will be only finitely many there'll be only finitely many points where it's supported. You take those away, and then it's going to be free along everything else. So this step, so this condition B being satisfied is exactly what the BSV conjecture or this weaker one that I stated will buy you. So okay, I think that's fine. I'll stop there. I think that's good enough. So thank you for listening and for your attention, and for the invitation.
Thanks. Any questions from the room? What was your last slide?
Oh, the last slide. Sure. Let me get there. So basically, so the first step is to say that, this magic quasi-isomorphism that we have, it also it does exactly do the Fourier transform that you want. So it says that Q over here acts as the DDT operator over here. You look at the version where you have negative powers and you complete with respect to you, you get a quasi-isomorphism like this. So really, there is a version of one of these deformed cyclic homologies with negative powers will be exactly the Fourier transform of the connection in the T direction. And then finally, the last step is to say that when you remove finitely many, how do you basically finish the proof? Again, you're going to use one of these conjectures, and you're going to say, okay, I can find something where you're smooth when you localize, and so that this module here, because when I invert Q, I get something that's completely acyclic, because it's basically a finite dimensional thing over C adjoins Q inverse. So by the same reasoning, I can make this one acyclic by inverting some polynomial, and then using the theorem on the previous side. If I look at the negative power part of Q, that's going to be the Fourier transform of the Gauss-Monen connection in the Weintraub-Bologodsky sense of this one here. So we can apply the non-commutative monodromy theorem to the negative part, but because this complex is acyclic, the positive part and the negative part are isomorphic at that point. And that's the key, because the positive part is exactly going to be the localization of the Gauss-Monen system. You start with the thing which is positive powers of Q, and you localize it. Basically, there's some subtlety due to U completion, but basically you can imagine, it's plausible at least that the thing localizes correctly. So that's how the proof is supposed to go. That's the last step. So it basically uses some very nice, some very lucky, let's say, that's how I mean it, some very lucky algebra that works out really, really nicely. And then all of these constructions of the Gauss-Monen system sort of give you exactly what you want. So yeah, so that was my last slide.
Okay, thank you. Other questions from Zoom? Any questions? Okay, well, let's thank Dan again.